Today we have problem 4 from part 2 of the UMD 2025 math competition, where we're reminded of the size notation of a set, right? And then we're also given that a collection of subsets S sub 1 to S sub x of 1 to 2025, the integers, is awesome if every subset has a size of 5, and for each pair of subsets in this collection, the size of their intersection is 1. So they only have one element in common. And so we essentially want to find the maximum size of a collection of subsets, or a awesome collection of subsets. And so surely a maximum awesome collection uses every single number in 1 through 2025, right? So, if we were to try to construct one, that uses if we were to try to construct an awesome collection that uses every single number, what would that, look like? And one idea is to just make one element to satisfy the second condition, just make one number in every single subset, and then distribute the rest of the numbers among them, right? So, for instance, we can make this shared number 2025, and then just order the rest of the numbers in each subset so that each subset size is still 5. So this might be S1, this might be S2, 5, 6, 7, 8, right? S3 will just be 2025 to 9, 10, 11, 12. And we go on until we get the subset of S sub x. The last one will be 2025, and then 2021, 2022, 2023, 2024. Right, and so in this, example, we do have that, each subset only has 2025 in common, so the intersection has size 1. Each subset still has 5 elements, and it uses every single number from 1 to 2025, right? And so how many subsets is this? Well, we have, 2025 numbers minus 1 due to choosing one number to be shared, and then among the rest of these, we split it in groups of 4 for each subset, right? So in total, we have this as 2024 over 4, which is 506. And so given this example of an awesome collection, we have that x is at least, or x is at least 506. 506. X is at least 506 because we have exhibited an example of an awesome collection of size 506. And so really the only way x can be greater than 500, strictly greater than 506 is if, we're able to play around with these intersections such that, it's not just one element that's in every single one, but maybe like somewhere in between you have like a 12 and then some other sets. But you just want to play around with the intersections in some other way to, I guess, have enough space to fit some more subsets in. But that seems, hard to do. So you might want to wishfully think that, maybe 506 is the limit. So we want to show that x is also upper bounded by 506. So then we can conclude that x is actually exactly 506. And we can do this by, we can upper bound x by, looking at this, the intersection, or the number, any number that is shared between any two subsets. And so let's define R sub n to be the number of subsets containing n. Then there's really two cases that we want to consider. Case one will be that there exists an R sub n that is greater than or equal to 6. And you see that choosing 6 is sort of natural because, I guess first, without loss of generality, we can let R sub 1 be greater than 6 because we can just always permute the numbers, uh, permute it in a way such that the number 1 is the number that is shared in more than 6 subsets. Then, we'll have, if it's greater than or equal to 6, then there exists some subset of 1 or 6 subsets with 1 in all of them. And then again, by permutation, we can just imagine the other numbers are just in order: 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Right, and we can do this because of permutation. We can just permute the numbers until we get to this. But the point is that all of these numbers have to be different, right? Because all of these subsets will intersect at 1 already. So then we want to consider, another subset T in an awesome collection such that 1 is not in T, right? Then when we look at the intersection between T and all 6 of these subsets, because 1 is not in T, T must intersect this first subset and one of these 4 elements, the second subset and one of these 4 elements, and so on, right? The last subset and one of these 4 elements. But that would require the size of T to be at least 6, right? Because of the fact that all of these elements are different. So example, if we try to build T to intersect the first subset at one point, it'll have to be one of 2 through 5. So let's say it's 2. Then the second subset, let's say it'll intersect at 8. The third subset will intersect at, say, like 12. And then the fourth subset at 17. The fifth subset at like 19. And the sixth subset will have to intersect at, let's say, like 25. But remember our other condition where the size of each subset has to be exactly 5. But we see here that if, such a number exists, such that it is part of more than 6 subsets, then any subset that doesn't contain it, in this case 1, will need to have size greater than 5. So the size of T will be greater than or equal to 6, which is a contradiction. So what this means is, if there indeed exists an R sub n greater than or equal to 6, then actually we have n is in every subset. Um, and because, right, in our example we made at the beginning, 2025 is our n in this case, right? It is in every single subset, or 506. And because this is maximum, because we use every single number, we have that in this case, x is indeed less than or equal to 506. Okay, so what about the other case, right, which is the opposite of this? The opposite of that statement, that there exists an R of n greater than or equal to 6, will just be R sub n is less than or equal to 5 for all n. And again, we want the upper bound, and we're given this already sort of upper bounded-ish condition on each R sub n. So I guess we're looking for an expression that involves all of the R sub n so that we can upper bound it directly using this fact. And the quantity that we want to look at is actually just the total number of intersection points. Right? If there are x subsets in the awesome collection, and each pair of subsets has to intersect at one point, then there are just x choose 2 intersections. But we can also look at it as, each intersection will be at a number. So for each number, how many pairs of subsets will it be the intersection of? And then if we sum all of those, that should equal the total number of intersections, right? So for each number from 1 to 2025, how many pairs of subsets will it be the intersection of? But that should just be exactly R sub n choose 2, right? For every subset that it's a part of, any pair of those subsets will intersect at exactly that one point. And because it is unique, because of this condition, each pair intersects at exactly one point, we have that there's no overlap or no double counting. So just summing over all numbers from 1 to 2025 and counting which pairs of subsets that will intersect at n, which is R sub n choose 2, will equal exactly the total number of intersection points, which is x choose 2. Then now we can see we can use our sort of condition here. Each R sub n is less than or equal to 5. So this implies that R sub n choose R sub n choose 2 is less than or equal to 5 choose 2, which is equal to 10. So now x choose 2, which I guess rewriting it as the sum, will be less than or equal to the sum from 1 to 2025 of just 10, right, which is 2025 or 20,250. So now solving for x, we have that x times x minus 1 over 2 is less than or equal to 20,250. So using the quadratic formula or any other method to solve for x, we can see that x is less than or equal to 506. Or sorry, x is less than or equal to 201, which is less than or equal to 506. So right in the second case, we still have that x is less than or equal to 506. Therefore, in any case, we have that x is less than or equal to 506. But we showed that x is also greater than or equal to 506 via our example up here. our initial example. Um, so therefore, we have that x actually is exactly 506 as a maximum awesome collection size. And that solves the problem.